Okay, now we are going to learn about probably the most popular sorting algorithm. Uh, it can be the favorite sorting algorithm of your interviewer, so you need to know every minute detail about it. Okay, and that is based on this merge procedure, merge sort. So guys, this merge sort, it operates on the philosophy of merge process only. And it utilizes this merge process intelligently. Okay, it utilizes the merge process intelligently. Now we will understand how to utilize this merge process intelligently, but before utilizing merge process intelligently, let us try to utilize it in a bit stupid manner. Okay, so let us see how that happens. So let's say an array is given to us, 7, 6, 5, 4, 3 and 2. Okay, so what you can think of it is, see, all of you remember insertion sort. Okay, so I am going to give you a glimpse of merge sort from very back. I'm going to give the glimpse from insertion sort itself. So let us try to understand. In insertion sort, there used to be an array, there used to be a prefix of the actual array which had got sorted, isn't it? Which had got sorted correctly, and then you used to consider a new element A3. Okay, and then somehow you used to make everything from here to here look sorted, isn't it? Yes, no? You try to position A3 at its deserving place, and that is the way you actually made everything from A0 to A3 look sorted. So is this not something like merging this with this, isn't it? That there is a subarray of size 3 or 4 or 5, and that is being merged with a subarray of size 1, right? So insertion sort was also in a way kind of merge sort. So somebody noticed this thing in insertion sort. Somebody noticed that, hey, it is doing that thing only, but can I do it a bit intelligently? Okay, and then he got a spark in his head. How he got? So here he said that, hey, what you are doing is something like this, that first this is your array 1, okay, and this is your array 2, and then you merge them. So how much time will you take to merge two arrays? What was the time complexity of merging two arrays? It was order m plus n, which is total number of elements involved in the two arrays, right? So currently the total number of elements involved is 2. So here your time complexity was order 2 in this step to make it look like 6, 7, 5, 4, 3, 2. In the next step of insertion sort, this was your array 1 and this was your array 2. So what was the time complexity in this approach? How many comparisons in this approach? 2 plus 1, 3. Number of elements, which is 3, right? So then it was order 3. And then you made it look sorted. In the next step, this was your array 1, this was your array 2. Time complexity, number of elements here, number of elements here, order 4. So you first did order 2 comparisons, then order 3, then order 4, eventually till order n. So this would be something like order of n square. Okay, so he noticed that the stupid thing that we were doing over here was that we were always trying to merge a very large array with a very small array. If you are merging a very large array with a very small array, the resultant array will have a size which is n plus 1 only. So what I mean by that is, if let's say the size of this is x, okay, size of this definitely will be 1. So after x plus 1 comparisons that you have done, the result that you got is a sorted array of size x plus 1 only. But can you do something where the merge process gives you a sorted array which is of size greater than x, right? So here the merges that you are doing, since you are merging a very large array with an array of size 1, what you are getting is of size x plus 1 only. My point is, why not try to merge a sorted array of size x with another sorted array of size x? What will be the resultant array size that you will get after merging these two? What will it be? It will be 2x, which is 2 times the size of original array. I very well understand this thing, that the number of operations here will be 2x, which is greater than this. But see, the result that I'll get, that will be very large. And now just think of it in this way, that let's say there was another array of size x, 2 more arrays of size x and x here, and you merge them. So what you get is a subarray of size 2x. Now you can merge them and them both. Okay, it will take 4x time for you to do it. Okay, but what you will get in the result, that will be of size 4x. Okay, so this was the philosophy, that instead of every time merging a very large array with the smallest possible array, why not keep on merging the arrays of equal sizes? Okay, now let us try to do that. Now let us try to do as I have just said. So what he decided was, he said that, hey, let's say I have something like this, 7, 6, 5, 4, 3, and then let's say 2, 8, 7, 6, 5, 4, 3, 2, and 1. Let's say this is what I have. Okay, so he said that, hey, first I'll merge all the subarrays of size 1, 1. So I'll merge this with this, I'll merge this with this, I'll merge this with this, I'll merge this with this. Okay, can I merge this with this? Can I merge this array with this array? What is the most important criteria for you to merge array 1 with array 2? What is the most important criteria? When can you merge them in linear time? When they are sorted. Can I say that an array of size 1 is always sorted? Yes, an array of size 1 is always sorted. So first I'll merge these two sorted arrays. When I'll merge these two, as a result of that, I'll get 7, 8. I'll do the same thing here also. I'll merge these two. As a result of that, I'll get 5, 6. Same thing here. Result of that, 3, 4. Same thing here. Result of that, 1, 2. Right? Okay. So can you tell me total number of operations done over here? In this step, what is the total number of operations done? It's not 4, it's not n by 2. You can tell me exact number. So to merge these two, size of this plus size of this, 2 operations. To merge these two, 2 operations. To merge these two, 2 operations. To merge these two, 2 operations. So 8 operations at this level. Right? Somebody said order 1. It's not order 1, right? There are many subarrays of size 1 each, and now you are making pairs out of them and then you are merging them. Okay. Now let's say you are on to the next step. Now the thing is, the way you were able to create here the pairing of sizes 1, 1, you can create here pairing of sizes 2, 2, because this is also sorted and this is also sorted. So this can be merged with this. This is also sorted and this is also sorted. So this can be merged with this. So this way, so you see the power of this. First you merge all the, so this is like a fusion reaction, right? First you merge all the subarrays of size 1, 1 each. Then when this entire thing is done, then you have the parts of array which are of size 2, 2 each, and now they can be merged. Now when you merge them, let's say you have merged them, you will get 5, 6, 7, 8. And you will get here 1, 2, 3, 4. So this is also sorted and now this is also sorted. Okay, cool. So let's talk about this step. How much time would this step have taken? How many comparisons over here? Tell me the right answer this time. I want you to start being consistent. Guys, if you are merging 2 arrays of size m and n, what is the time complexity? What is the time complexity when you are merging 2 subarrays of size m and n? M plus n. So use the same thing over here also, na? First you merged these 2 subarrays of size 2 and 2 each. So how much time here? How much time does this merge take? 2 plus 2, 4. How much time here? 2 plus 2, again 4. So overall time 8. Now when I come over to this step, what happens? That I have got 2 subarrays, okay? Both of them are of size 4 and 4 and both of them are sorted. So can I eventually merge this and this? I can do that. And if I do that, what will I get? My result will be 1, 2, 3, 4, 5, 6, 7, 8. Can you tell me total number of comparisons over here? This time make it right, again 8, right? So did you see that at the level 1 where the sizes were 1 1 1 each, there also 8 operations, here also 8 operations, here also 8 operations. And what is 8? 8 is the total number of elements. So at each level of fusion, the number of operations is order n. So now can you tell me the overall total number of operations that happened over here? What is the total number of operations that ended up happening over here? Why is that tough? 8 plus 8 plus 8, 24 operations, isn't it? Right? 24 operations. Okay, cool. So here total number of operations is 24. But if let's say you had used bubble sort or insertion sort, then how many operations would have happened? This is sorted in strict descending order. So you would have had n into n minus 1 by 2 operations. It would have been 8 into 7 by 2, which is 28, and this 28 happens to be greater than 24. Okay, so can you see this thing clearly over here, that the number of operations that have happened over here is much lesser than the number of operations that have happened over here. Not much lesser in this case because the number of elements is very less, but it is lesser. And now let us try to understand why is that happening. So we'll all understand that. So look at it as a tree which has a root over here. So this is the root. Okay, so generally you see a tree like this. Now I am going to reverse it. So this is the root, and this is left child, this is right child. Now for this is left child, this is right child, and so on and on. And then there are children. Can you visualize the kind of tree that I am asking you to visualize? Right? Okay. So what is the height of this tree? How many levels are there? In short, how many levels are there? If the number of nodes is n, if the number of elements is n, how many levels are there? Log n levels. And how can I say log n levels? Because in this level, the number of elements in every subarray is n. In this level, the number of elements in every subarray is n by 2. Here, in every subarray, it is n by 4. So the moment it becomes that every subarray has a size 1, that would be the last level. So every time number of elements is reducing by half. So if I do n upon 2 raised to power I, where I is number of levels and equate it to 1, then I will be log of n base 2. So total number of levels will be nothing but log of n base 2. How total number of levels will be log of n base 2? And what is the number of operations at each level? N. So since there are log n base 2 levels and number of operations at each level is n, what will be the time complexity? It will be n into log n base 2, right? So yeah, and you also realize that why is it much more efficient than others? Because others like insertion sort are doing something like merge only, but every time they are doing it with a very large array and with an array of size 1. Here the power is of exponentiation. The power is of exponentiation. So first you make subarrays of size 2 2 2, then you make subarrays of size 4 4, then 8 8. So this way you start with all the independent elements, and when you perform this fusion, the number of levels is very small number of levels, and because of that you end up doing just n log n base 2 operations, and that is the reason this merge sort is very very fast. Yeah, in insertion sort number of levels could be n, because at every time your sorted array size will just grow by 1 unit. Okay, cool. Yeah, another thing that I want to ask over here is, no, I would not like to ask, I would like to show. So see, now this is going to be very important. This is a subtle observation, but this will help you solve very tough and tricky problems. Okay, really tough problems. So see, what is happening over here is, let's say this was my original array. Okay, then what happened was, by the time the operations of this level were completed, the elements which are over here are jumbled somewhere over here only. So what I mean by that is, it did not happen that at the next level 7 came at here and 4 came at here. So if you are merging this and this, the elements will remain somewhere in this and this only. So 7 came here, 8 came here. Similarly here also, so 5 came here, 6 came here. If you take a look at this level, so I draw a line between 8, 7, 6, 5. So although 8, 7, 6, 5 got permuted to 5, 6, 7, 8, but that permutation is of these elements only. That permutation is not of these elements or these elements or these elements. If you're not getting, you will get later, but if you get fast, that is good for you. Okay, so again, I will say it again. If let's say I draw a line between these elements and these elements, okay, so by the time I am here at this level, okay, then everything over here is present here only. It never happened that something over here went this side or something over here went this side. It never happened. Of course, when everything got sorted, then it happened. But as long as there was a distinction between these many elements and these many elements, this was just a permutation of this, and this was just a permutation of this. And this will be a very helpful thing. Okay. So guys, whatever I told you, can you write the code for this? Can you write an iterative code for this? You can very easily write an iterative code for this, isn't it, guys? So how many iterations you will have to run? You will have to run log n iterations. So you can have an outer for loop which runs for log n times. Now in the inner for loop, in the first step, you will merge all the subarrays of size 1, 1. In the next iteration, all the subarrays of size 2, 2. Then all the subarrays of size 4, 4, and so on. You will get your job done. So this way you can write an iterative code for merge sort. Those of you who have never written iterative code for merge sort, it would be my strong advice that if you write it, you will get immense clarity over how merge sort operates. Okay, so sometimes it can happen that you do not have elements in power of 2. So let's say you have elements like 8, 7, 6, 5 and 4. Okay, so can somebody tell me what would you want to do over here? You have to update in original array. Yes, you have to update the original array itself. You have to sort the original array itself. But that's a good question. Now tell me one thing, guys. To do all this work, would you require some extra space or not? Yes. And why would you require that extra space? Because you would want to perform merging in linear time. If you have to perform merging in linear time, for that you would require additional auxiliary array where you will first put the merge content of this and this, and then you will copy back that merged content to the original array. So you would definitely require an auxiliary array which you are using for performing the merge task. Okay, and you can just have that auxiliary array declared globally, and you can use it at every level. Okay, you just need to ensure that the two sorted arrays that you have at any point of time, they are getting merged at a different location, and then you copy back that from there to the original array, right? So you can try this out iteratively and get it done. By the way, I can do it recursively also, and recursive approach is a very popular approach. So let us all try to understand that as well. So the point that I was trying to say before, that there can be elements which are not in power of 2. So here what would you want to do? So here what you can do is that if you are making groups of, let's say, this, then this poor child might get left. So what you can do is you can consider this with this. Okay, so that adjustment you should be able to do so that nothing gets left over. Just include it in along with someone. It will not increase the size by a lot. At max it can increase the size by 1 unit, and that's it. Can you make that adjustment while writing the code? It's very easy. You can try that out. Okay, yeah. So now let's come to something like this. Now how we can perform merge sort in a recursive manner. So you all know this, so recursive approach will be very easy. So see, merge sort is a class of algorithm which is called as divide and conquer. How many of you have heard about this divide and conquer? And the only reason I am introducing this is because it is immensely important, and this will prove very helpful at later stages also. So just think of it like this. In divide and conquer, what do you do? That there is an array, or there is a problem, there is a big problem, and let's say the problem is in form of an array. So what you do, you break it into two parts. Okay, you break it into problem P1 and then problem P2. So this breaking thing is called as divide part of divide and conquer. Okay, now when this problem is solved, it will return its solution 1 to its parent. Okay, what is the parent? Parent is the recursive function that invoke these children recursive functions. Okay, similarly, when this is over, it will return its solution S2, and now once S1 and S2 solutions have been received by it, then it can conquer it. So conquering means doing something with S1 and S2 to find out the solution for this entire thing and return that solution to its parent. I think I had talked about it while teaching recursion also, isn't it? Did I talk about something like this over there? Yeah. So see, that thing comes very useful, very handy over here. Yeah. So if you try to understand, then merge sort is doing something like that only. Okay. The difference between this and this thing is that this was a tree which was like this, where the root was at bottom and leaves were at top. Here, the root will be at top and leaves will be at bottom. So this iterative approach was a bottom to top programming strategy, and your recursive approach will be top to bottom programming strategy. But effectively it will be the same. Okay, let us all try to understand. So think of it in this way, that there is an input array. Okay, now that input array you want to sort. So first what you did was, you tried to, let's say this was the array from 0 to n minus 1, you want to sort it. So first you tried to sort the half of it, which is from 0 to m, okay, and then the other half of it, which is from m plus 1 to n minus 1. So by the time this function exits, this would have got sorted. By the time this function exists, this would also have got sorted, right? Now the final thing that you can do is, you can merge the two sorted parts. Okay, so just think of it in this way, that this now this is eventually sorted. So let me give you another example. So let's say you have an array that contains 8, 7, 6, 5, 4, 3, 2, 1. So what you can do is, you can call a function to just sort half of your portion, which is 8, 7, 6, 5. And then you can call another function to sort the remaining half, which is 4, 3, 2, 1. Okay. So by the time this returns, what would have happened is that this would have got sorted. Okay, and you would have, somehow there was something magical that happened over here that sorted it, and its sorted version would be 5, 6, 7, 8, which you would then copy over here in the original array. And the same thing over here, something magical happened that sorted this and copied that sorted portion over here. Now this part is also sorted and this part is also sorted. So the last thing that it can do is, it can merge this thing with this thing, and it can do that in linear time. Okay, because this is n by 2, this is n by 2, merging them would be order of n. Okay, so let me just rewrite it. 8, 7, 6, 5, 4, 3, 2 and 1. Right, now you will call for your left subarray, you will call for your right subarray, and then the last part will be to merge. Now first this instruction will happen, then this instruction will happen, then only this instruction will happen, and it makes sense because I can merge the two things only when both of them have been sorted, right? So this comes at last, right? So divide, first divide and then conquer, right? Now again, at the level of this, what will happen? It will get broken into 8, 7, 6, 5, and now when both of them are over, it will try to merge it. Now again, at this level, it will break it into two subarrays of size 1 and 1, and when both of them are sorted, then it will merge it. What will happen at this level? Can somebody tell me? So first this will call this, this will call this, this will call this. So can you tell me what will happen at this level when you just have one element left? Would you want to go down further from there? Can I say that an array of size 1 is an already sorted array? Can I say it? Yes. So since it is an already sorted array, so no need of going down further. You can simply return. So you can just simply return and not go down from here, okay, because this is already sorted, okay, because the moment you call function for something, the responsibility of that function is to just sort this much. So here the responsibility of function is to just sort this much, and this much is sorted. Similarly, this much is also sorted. So the next instruction to execute will be merge. So now when it tries to merge, now try to understand one thing very carefully. This 8 is present at index 0 and this is present at index 1, right? Now you are trying to merge two sorted arrays, 8 and 7. Do you need an extra space for merging it or not? You need an extra space, right? You definitely need an extra space. So just imagine that there was an extra space of size 2 and then you had a pointer here, you had a pointer here. You saw this was smaller, so you placed this here, and then this array was over, so then you place this over here. And now you have 7 and 8, and after you have 7 and 8 in an auxiliary array, then you can copy this back over here. So what will happen now is that now this will get converted to 7 and 8. Okay, so by the time this entire function is over, this has got sorted. Same thing would happen at the level of this also. So this would have called for 6, 5, this is already sorted, so it would return, this is already sorted, it would return, and now merge would kick in. So when merge would kick in, it would merge this with this using that auxiliary array and copy that 5, 6 over here. Now this is also over, this is also over. So for this parent, both the children are done executing. So now merge will happen. So it can merge now this with this. Why? Because this is also sorted and this is also sorted. For that, it will need an auxiliary array of size 4. And it can easily merge this with this. So it will have 5, 6, 7, 8. And then it can copy the contents of this over here. 5, 6, 7. So this is the most important part, where for merge thing you are using auxiliary array, and when the merge is done, then you are copying it back to the original array. Okay, now you answer me one question. To do all of this, will you want to create a new auxiliary array at every step, at every recursive function call? Will you want to create a new auxiliary array everywhere? Because here you needed an auxiliary array of size 2, here you needed an auxiliary array of size 2, here you needed an auxiliary array of size 4. So would you want to create a new auxiliary array at every parent level? It's not needed, right? I can get it done using a single array also. How? I can have that single array declared globally. Can you tell me what should be the size of that single array? What should be the size? The size should be n. And why its size should be n? Because at max, I will be merging two subarrays of size n by 2, n by 2, and its size would be n in the auxiliary array. So every time I will be using it, it's just that the elements will get overridden, okay, at different levels. Okay, so this is how it will go ahead, and this is how you can open up this branch also. Okay, so this gets broken into 4, 3, 2, 1, 4, 3, 2, 1. Yeah, then merge here also after this merge, and here also after this merge. So even if you take a look over here also, what is happening clearly is that even in this case, if you see this thing, the thing that happened was that the number of levels are again log of n base 2, because the size is decreasing by half every time, right? And at every level, so here you merged two subarrays of size n by 2. So n by 2 plus n by 2 order n time. Here you merged 4 subarrays of size n by 2, of size n by 4, n by 4, and n by 4, n by 4. To merge this and this n by 2 time, to merge this and this n by 2 time. So n by 2 plus n by 2 again order n. So at each level order n work, and that's the reason it is order n log n. How many times one element gets overridden? Why do you want to know answer to that? You figure that out on your own. Okay, it is not important. Okay, so the most important thing is that the same array is being used. Okay, so I can use that, right? Because are you getting it? Yes, no? I can use that. I can use it at this level also, and I can use the same thing at this level also. The element gets overridden, what do I have to do with that? I don't care, right? So how many of you can write code for this merge sort? So maybe I'll very quickly write it. So the reason I am writing is because I consider this as a very important algorithm. You know, it will help you solve very difficult questions. So tell me, there will be a merge sort function, right? So let's say there is a merge sort function. Should it have a return type? Should it have a return type? No. It can take the array by reference and simply sort that array and return. So let it be void. Can you tell me what will be the arguments to it? What will be the arguments to merge sort function? What all things would you want to pass? Definitely you would want to pass in the original array. And what else will you want to pass? The starting and ending index, right? Because see, this merge sort is calling itself recursively, right? But when it is calling itself recursively, it is just passing a segment of it, a portion of it. So how does it denote a portion of it? By passing the subarrays starting index and ending index. So it is important for me to pass the starting and ending index, so that I can always find the m, which is I plus j by 2, and then recursively call merge sort for I to m and m plus 1 to j, right? So it will take I, it will take j, and that's it. So what is the first line of code that you write? You always write termination conditions first. So what will be my termination condition? How do I even detect that it is my term? When the length is 1, but I'm not passing length. So how do I check that? I can just compare I and j. When I and j are same, then I can say that, hey, now this array is already sorted, so please don't go down further. So if I is equal to j, what should I do? If I is equal to j, I should simply return so that the control passes to my parent, and then the next operation happens. Okay. So if I is equal to j, I should simply return. Otherwise, what will you do? Otherwise, for any other case which is not falling in this category, you would want to break. To break, you would want to find the mid. So int m equals to I plus j upon 2, right? Now once you have mid, then you can partition it into left and right array, right? So how can you do that? So you would want to invoke merge sort for your left part, which is from index I to m, okay? And you also want to invoke merge sort for your right part, which is from m plus 1 to j, right? So these two lines of code would magically ensure that this thing and this thing have got done. And it's not magic for you now, because it's all happening recursively, right? Recursion happens in depth first manner. So this will call this will call this, now this will call this returns, this will call this, that also returns, sorry, this would have called it returns, then this would have called this, it returns, then merge happens, then control comes here, then this calls this. So you know how it all happens because you know recursion. Okay, what should be the last line of code? So this was the divide part, now the conquer part should come. So what should be the last part? The last part should be to merge the two sorted arrays, okay? The left portion and the right portion are sorted in themselves, so I need to merge them. So I will want to write a merge function where I'll pass this array, and I'll pass the segments of the array which are sorted. So from I to m it is sorted, and from m to m plus 1 to j it is sorted. So now this merge process should treat this as one independent sorted array and should treat this one also as another independent sorted array. Every time what will happen, that the merge function that you are calling, it will be called for segments like this, or this, isn't it? Because of this nature, because from I to m everything is sorted, and from m plus 1 to j everything is sorted. Okay, now let us talk about that merge function. So merge function, does it need to return anything? No, it just needs to perform the merge in place within the same array. So what all will it take? It will take the array, it will take the starting point of first sorted array S1 and ending point of first sorted array, starting point of second, ending point of second, so S2 and E2. And now it will have some logic contained inside which will be responsible for the merge. Okay, so yeah, to perform the merge, do I need an extra space over here? The answer is yes, I need an extra space. So from where does that extra space appear? Would you want to initialize a new array inside this every time? Would you want to do that? Take my word, never do that. Why you should never do that? Because if you do that, it would end up consuming lot of memory, isn't it? Yes, no. It would end up consuming lot of memory, right? So what you can do is, you can just have a global auxiliary array of size n. Why size n? Because the maximum number of elements that you would want to merge would be n and never more than that, right? So what you can do over here is that treat this as your index I, treat this as your index j, okay? So you can initialize I to s1, you can initialize j to s2, okay? And then what you can do is that you can have k, and this k, you know why I am declaring k? Because you want to sort the contents of this and this in another array, right? So can you tell me how should I initialize my k? So I'll suggest one way to initialize your k is that you want that everything from S1 to E2, because they are continuous segment because of this and this, everything from S1 to E2 should get sorted and should get copied into the original array from S1 to E2, right? This is what you would want. Okay, so what you can do is you can somehow manage to store the sorted form of elements from S1 to E2 in the index from S1 to E2 only in the auxiliary array, and then copy back that auxiliary array to the input array, which is your original array. So I would initialize my k equals to s1, okay? So my k is equal to s1, and now comes the logic for merge. So for I is already initialized, I smaller than equals to e1 and j smaller than equals to e2. Now the code comes that if I see that array of I is smaller than array of j, if I see this thing, if array of I is smaller than array of j, then what would I do? Then in my auxiliary array at index s1, sorry, at index k, yeah, at index k, I'll write auxiliary of k plus plus equals to array of I plus plus. Else I'll do auxiliary of k plus plus equals to array of j plus plus, right? Okay, but is just this much enough? Is this much enough? No, because it could have happened that, let's say these were the two arrays and I was able to ensure that all these come here, but from here just these two came and this element got left. So I need to write a code for that, just like I wrote in the beginning of the class. So I'll write for I lesser than equals to e1. So if at all some elements of first subarray were left, then they should be given their due positions in the auxiliary array of I plus plus. And the same thing for the other array. If at all the elements of second array got left, then they should be given their due position in the auxiliary array of j plus plus. Is it done? Is it done till here, or do I have to take care of something? Is it done? Is the merge successful? Yeah, the last step should be to copy. Yes, and I should copy what? I should copy the contents of auxiliary array from the same index to the same set of index. And how can I do that? Very easily. I can run a loop from I equals to s1 to e2, and I can simply say that original array I equals to auxiliary of I. That's it. This much. And now you can see that this thing which is running at each level can very easily run with the same auxiliary array. It's just that its values will keep on getting overridden and my job will get done. That you think on your own. It is not, but at any point no more than n size array will be created, and after merge is done, that array will be destroyed. So why will be the case that we consume a lot of memory? Okay, see, whatever you are writing that array will be destroyed, I'm just going to talk about that line. It is not necessary. You cannot take it for granted that array will be destroyed. Why? Because what usually happens is that if there is a variable which is not under your reference, that usually gets garbage collected. Now garbage collection is automated in languages like Java, but it is not automated in languages like C++. Okay, so you cannot take it for granted that it will get destroyed for sure. Are you getting my point? So until unless you yourself are destroying it, you cannot say that it has been destroyed. Okay, did you get my point? Yeah. And even if you are destroying, then let us try to understand one thing. What will be the tell me, what will be the maximum stack size? What will be the maximum recursion stack size of this merge sort? Don't you remember? Yeah, it will be log n, right? So what would happen? This function would have created an array of size n and would be waiting for this to complete. This would also have created an array of size n and would be waiting for this one to complete. This would also create an array of size n. So at any point of time, you have got log n functions waiting in the stack, and everyone has their own arrays. Okay, so you would at least have n log n size with you. Did you get my point? Yes, no? Right? So no matter, even if you are destroying them, then different function calls having created their own copy and storing them somewhere, they would end up, utilizing that much of space. Okay, so a better idea is to simply have a declare a global auxiliary array and use that as and when required, right? Just the values are getting overwritten, and that's it. Somebody asked question about power of 2. I don't care. Again, like, it's not a big thing. See, even if it was like 0 and it was like 2, what would have happened? Let's say you had 5, 7 and 4. You would have broken it from 0 to 0, which is just this, and index 1 to index 2. So this would simply have returned, but this would have gone on to 7, gone on to 4, okay, and then this would have returned, and then merge would have happened. Merge would have converted this to 4, 7, and then whatever it has this as sorted, it has this also as sorted, this is sorted, this is also sorted, so it can do its job. So unequal division would happen, but that would not hamper the correctness of your algorithm. That would not hamper the runtime of your algorithm. Memory is declared when we call merge function or in the recursive call only. Are you talking about memory of auxiliary array? So auxiliary array, if you are declaring it globally, then it happens even before you make the function call, right? It happens immediately during your compile time itself. That during your compile time, the array was global, so the space got allotted for it. But if, let's say, you are declaring it in the runtime, so let's say you can declare a vector in the runtime, or you can even declare a new array using pointers in the runtime. In that case, also what would happen, if there are, let's say, log n functions waiting for each other to get executed, all of them would have created their own auxiliary array of size n, and they would be there in the memory. Okay, they would be present there in the memory, they would be occupying memory, right? So that is not so memory efficient. Can we copy auxiliary array to original after all the recursion call complete? Think about it. I think you sound a bit confused about it. I'm not sure how would you do that and why would you want to do that? Because your auxiliary array is always changing, right? When it moves to the next level, it contains the sorted portion of that, so it won't work like that. How in compile time if I am giving size in runtime? Yeah, so it totally depends. No, like if you are, let's say, declaring a global array, can you declare a global array like this? Yes, no, can you do that? You can't do that, because if you're declaring something globally, you have to give it its predefined size. Okay, yes, n is not known, but if you are taking the input in the runtime and then you are declaring it, then that's a different thing. Then that's a kind of dynamic memory allocation only. Okay, you are not doing that using pointer, you are doing it very intelligently by writing this kind of thing, but this thing internally uses pointer to do that, what you want. Okay, so first of all, are you all clear with the merge sort now? Very clear with how it works, both the things, bottom top and top bottom? Yes, no? Guys, don't you think this top to bottom is just a misnomer? In top to bottom also, what is happening from bottom to top only, isn't it? Whatever is happening, that is happening from bottom to top only. Just for, giving a good look to eyes, it is being showed as a beautiful tree and top to bottom. Okay, cool. Lastly, I would like to ask one more question, that here, what I was doing, I was breaking this array into two parts and then merging it. Can I break the array into three parts and then merge it? So this is like a binary merge sort. Can I think of a ternary merge sort where I am breaking my array into three parts and then merging it eventually? Will something go wrong? Is it algorithmically correct or not? According to me, it is correct. Okay, next question. Is it more efficient or less efficient? Okay, why is it less efficient? Can somebody tell me the exact time complexity of it? What is log base 3 here? Okay, so let us try to understand that, guys. Okay, I am asking you one simple question. There are three sorted arrays of size n by 3, n by 3, n by 3. Don't be in a hurry, you will give me wrong answer. This is the last thing we are doing for the day. Okay, so just focus your attention very clearly. This was asked to one of my friends in his Google interviews. Okay, so there are three sorted arrays of size n by 3, n by 3 and n by 3, and I want to merge them into a single sorted array of size n. Okay, in how much time can you do it? In how much time can you merge three sorted arrays of size n by 3 each? So how are you planning to merge? Are you trying to do something like this, that you will first merge this and this, and whatever will be the result of this, that you will then merge with this? Are you planning something like this? Yes, no, right? So it makes sense. You should plan something like this only. But if you do that, can you tell me the complexity of just this step? Just this step where you are merging the two subarrays of size n by 3 and n by 3. How much time is consumed over here? Why does that take a lot of time? It should be 2n by 3, right? 2n by 3 time over here, correct? Now the result of this is of size 2n by 3. Now when you merge this with this, so how much time will this step take to merge that with this? It should be 2n by 3 plus n by 3, which is n, isn't it? So what is the overall time taken by you to merge these three? That is equal to 5n by 3. Okay, now how many levels will be there in the ternary version of merge sort? How many levels will be there? It should be log n base 3, isn't it? So log n base 3 number of levels will be there. That will be the height of your tree. And you will see that at every level, this much work will only be done. The way here at every level n work was done, in that at every level this much work will be done. You can try that out. Take a pen and paper, you can see that. Okay, at every level this much work will be done. So for that the time complexity will be this, 5n by 3 into log of n base 3. Now although the base has increased from 2 to 3, and that is a good news for me, but this has got incremented from n to 5n by 3. So this is a bigger increment. So because of that, this will be more time consuming as compared to binary version of merge sort.